All right, everybody, we are back and we are starting chapter 8. This is going to be our second consecutive chapter that really focuses on reactions of alkyl halides. And so, in the last chapter, we went over SN1 and SN2 reactions, right, of alkyl halides, nucleophilic substitutions. In this chapter, we're going to go over eliminations. If you guys remember from chapter, whatever it was, 3 or 6, I can't remember. One of the previous ones. Elimination is where we basically remove a couple of sigma bonded atoms from a structure and create one new pi bond. Okay? So we're going to see how to do that, and again, we're going to see it happen in a couple of different ways, a couple of different mechanisms, and then we're really going to see how the SN1 and SN2 reactions also tie into what we see with eliminations as well. You're going to see they're going to be very much interrelated. All right, well, let's start off with just kind of general information here, right? Let me show you generally how an elimination works. All right, let's just take something really simple. Let's take bromoethane, all right, 2-carbon alkane with Br on it. All right, what we do when we do an elimination is we have an alkyl halide, we have a base of some form, right? And this base can be neutral or it can be negative. Doesn't matter which one. Well, I guess it does matter, but you can do it with either one. I'll just use a negative one here. All right. And then you also have a special whole hydrogen over here I'm going to make a note of. All right. This carbon actually has three hydrogens, right? It's CH3. I'm just going to draw one of them to show you for background purposes here. All right. Within the structure of the alkyl halide, I want to identify a couple of different spots. All right. If you look at this carbon right here, the carbon with the halogen on it, that is going to be referred to as the alpha carbon. Okay? The alpha carbon. Any carbons that are directly adjacent to the alpha carbon, and in this case we have only one, will be called a beta carbon. Okay? We can have more than one beta carbon in an alkyl halide, and I'll show you that in just a minute. All right, and then also any hydrogens that are attached to beta carbons are referred to as, you guessed it, beta hydrogens. All right. So basically what happens in an elimination is that you're going to eliminate or lose the halide, right? The halide is going to act as a leaving group just like it did in the previous chapter. And we're also going to lose a beta hydrogen, all right? And in the process, you end up forming a pi bond between your alpha and your beta carbons. And you get Br minus as a waste product, and you get a protonated base. Excuse me. Okay? So yeah, elimination reaction of alkyl halides, you always lose a halide, and you also always lose a beta hydrogen. All right? All right, let me show you a couple of other ones. Let's grow it out a little bit from just 2 carbons. Let's try something like this. Try 3 carbon species. Let's try 2-bromopropane. All right. We can do the same thing here. We can set up, a reaction with a base of some sort. We'll just use a strong one again. All right. Same thing, right? Basically what you're looking for is you're looking for a halide. Hey, we got one with Br. And you're looking for beta hydrogens. All right. Now in this one, you'll notice there's actually 2 beta carbons right here, right? One on either side. And each of those beta carbons contains beta hydrogens, right? However, one thing about this is that just because you have 2 individual beta carbons, it doesn't mean they're any different from each other. It doesn't mean they're chemically different. And in this one, you can actually draw a line of symmetry through here, and you can see that, hey, this carbon, what it contains in its environment, is exactly going to be the same as this one. So, if you kind of translate that when you're drawing products, if you really wanted to take this literally and draw a double bond between the alpha carbon and each one of these beta carbons, you would get this and this, right? But if you look at these are exactly the same products. It's literally like you're just taking one of them and sort of moving around and looking at it from the other side. So this one still will only give you, one unique product, even though individually it does have more than one beta hydrogen and beta carbon. One thing that's going to be really new about this chapter is the fact that you are going to be getting some product mixes, though. We didn't see that in this reaction, but we can see it when we have more than one type of beta hydrogen. Not necessarily just different ones, altogether, but different types. So let me show you another one. Let's say we had this. By the way, we don't have to use Br for all of these. That's just the one that always comes to my brain. I'll just use Cl here to be different. All right, so let's say you're doing this. Okay, so we have our alpha carbon, right? Our alpha carbon has the chlorine on it. And we have two beta carbons, right? We have one here, and we have one here. And hopefully you can see that in this case, they're different from each other, right? The beta carbon on the left has a methyl group attached to it that the beta carbon on the right does not. So what that means here is you can actually get a mixture of alkene products. We could stick that double bond between those two carbons. Or we could stick it between these two carbons. And guess what? You get both, right? From here on out, you're probably going to be seeing several reactions that will give you product mixtures, which are kind of a hassle to deal with, not only in solving problems, but also in real life, right? Think about it. You're trying to get a really good yield of something, but you have a reaction that produces like multiple products. So you have to take that product, separate it out. You're always going to get a small amount, and then you have to figure out how to make more of it. But it is a fact of life, right? So yeah, this guy produces two different products here. And when we have product mixtures, oftentimes we can predict which ones will be present in higher amounts. In other words, we can have major and minor products. All right? For example, in this reaction, I can tell you that this one right here would be your major product. Now, how did I know that? Well, I used information that I have not taught you guys yet, so I wouldn't expect you guys to know it. But guess what? We're fixing to talk about it. All right. Whenever you're looking at the products of the alkene products of reactions, what we can do is we can follow something called Zaitsev's rule. Okay? Basically what Zaitsev's rule says in a nutshell is that the most stable alkene products in a given reaction are going to be present in larger amounts. In other words, they're going to be your major products. So you got to figure out, what makes one alkene more stable than another one, right? Just like we saw with carbocations before, when we say, something is more stable, that means it's easier to form. Okay? So let me talk to you about stability of alkenes. All right. The first thing that we have to look at here is what we call the substitution pattern, all right? And this is easiest to illustrate using the simplest alkene of them all, and that's ethene. Excuse me. All right? That is ethene. And you see it's basically just two carbons double bonded to each other, and each one of the carbons has two H's attached to it, right? This is our baseline. what we can do when we say we make a substituted alkene, that means we have a carbon group in place of one of these H's, right? So if we tweak this a little bit, I don't know, let's just put a CH3 right there. I've taken away one of the H's, one of these four H's, and I've made it into a monosubstituted alkene, right? Let's say I did it again with one of the other H's. Let's say I put a methyl group right here. All right? Since we've basically swapped out two of those H's, that's now a disubstituted species. Keep going. And it doesn't have to be CH3, it could just be any carbon chain, by the way. Now we've got three of them substituted. You can probably guess what that's going to be, right? That is going to be tri. And lastly, we can substitute out the other one, like that. That is a tetrasubstituted alkene. Okay, so you see there's several different substitution patterns that exist with alkenes. And as far as stability goes, the more substituted, the more stable it is. All right, so tetrasubstituted is more stable than tri, more stable than di, more stable than mono, more stable than ethene. So that's why when we're looking at these two products of the last reaction we went over, let me put these back up again. All right, and I said this one was the major one. Well, why is that? Take a look at the substitution pattern. Take a look at this carbon right here and this carbon right here, the carbons that are in the double bonds, and basically look to see how many H's do you directly attach to them, right? If these were unsubstituted, they should have 4 combined, right? 2 from each. Well, if you look at this one right over here, it doesn't have any, right? It doesn't have any H's directly attached to it. Those 2 H's have been substituted by a methyl group and then half of this 6-membered ring, right? Over here, we've got 1 hydrogen. All right, so that means 3 out of the 4 spots have been substituted, so this is a tri-substituted alkene. Excuse me. All right, if you look over here at these 2 carbons, well, if you look at them closely, each one of them is going to have an H. So that means this one's going to be a di-substituted. And as we've learned, tri-substituted is more stable than di-substituted. That means it's a lot easier to form. And that means it's the, sorry, I lost my train of thought. It is the major product in that reaction. Okay. All right, let's try another one. Let's say I had this. Okay. All right, well, again, first identify your alpha carbon. It's here. Then I'll identify any beta carbons that you have. There's one, and there's one. Make sure those beta carbons have at least 1 hydrogen, in which case they do. So that means you can get substitutions between those 2 carbons and those 2 carbons. All right, so those are your products. How would you figure out which one's major? Well, same thing we did before, right? Look at the substitution. If If you look at the substitution pattern on the one on the left, hopefully you can tell that there is a tri-substituted. If you look at the one on the right, hopefully you can tell this is a mono-substituted. Yeah, 2 H's over here and 1 over here. So that is mono-sub. So definitely that one is going to be your major product. All right, very good. All right, so that's one sort of, what's one factor that plays into these elimination reactions and determining major products. These are what we call regioselective. All right, and basically when I say if a reaction is regioselective, it means that certain constitutional isomers are preferred. Okay? Certain constitutional isomers are preferred. One thing that we can also see here, let me redraw this, is that alkene formation is also what we call stereoselective. That means that certain stereoisomers, I cannot spell today, that certain stereoisomers are preferred as well. All right? And let me illustrate what we mean by this. This is going to be sort of a bit of a new analysis of stereochemistry from what you've done in the past. All right? So we're sort of adding to it. All right, so stereochemistry of alkenes. All right, so let's say that we have this. All right, and we're specifically looking at forming a double bond between these two carbons. All right. Now, if you do this, we can get that. That's pretty easy, right? However, there's another alignment. There's another way we can draw the little zigzags, depending on rotation around this carbon-carbon single bond, right? We can get this, but we can also get this. This is what we call the trans form, and this is what we call the cis form, all right? And we talked about cis and trans with regard to rings, right? If you remember back in one of the previous chapters. If you had two substituents on the same side of the ring, what did we call it? We said they were cis to each other, right? If they were on opposite sides of the ring, we would call it trans. We see the same thing in disubstituted alkenes. Right? Frequently in disubstituted alkenes, you will have the opportunity for cis or trans isomers. Okay? So this is a disubstituted alkene, specifically disubstituted alkenes where you have one substituent on each of the carbons. If you have something like this, whoops. If you have something like that, that's disubstituted as well. But that is called a geminal or gem. All right. Whenever you have gem alkenes, there's not any difference in stereochemistry, so you don't have to worry about it. However, when the two substituents are on different carbons, then you do have to consider the possibility of cis and trans. Okay? So yeah, depending on where this little thing was, and it's, whoa, I didn't mean for the eraser to be on. Depending on where this was in the twirl, around the single bond, you might have happened to have, removed the halogen and the beta hydrogen while the substituents were in the trans position or in the cis. All right. There is another controlling factor for that, but we'll look at it later on in the chapter. All right. All right. So basically, when you're determining cis and trans, here's what you want to do. If you have a disubstituted species such as this, you know one of the carbons is going to have one H, and one of the carbons is going to have another one, right? And that's just a fact That's just a bare fact. You're always going to have that. Okay? What this describes is the relative positions of the two other groups to each other. All right? And the context for that is, where are they located relative to the double bond? Are they on the same side of the double bond, or are they on opposite sides? All right? Well, here is the double bond right here. I'll try to draw it in a rectangle to make it look a little different. Here's the double bond. You see this methyl group is pointed down, right? Literally going down in a zigzag pattern below the double bond, whereas this one is going up, right? So those were in opposite directions of the double bond, so we would say those two methyl groups are trans to each other. Whereas in this case, you see, the two methyl groups are on the same side of the double bond together, so that is referred to as cis. All right? And they don't have same stability. One of them is a little bit more stable than the other one. Can you guess which one? Well, if you follow the patterns that we learned with rings, you can probably figure out that trans is more stable than cis. Why is that? When in doubt, say steric hindrance. Yeah, these two methyl groups right here, these two R groups, they're closer to each other in the cis arrangement, so there's more crowding between them. Whereas when they're in trans, they're further away from each other. Okay? So, it is possible, certainly, within an alkene-producing reaction, for you to get more than one stereoisomer, for you to get a cis or trans, but when you do so, they're not going to be in the same amount. The trans should be a greater product than the cis is. This effect, by the way, is not as important as the stability of as the substitution factor. Right? So if you're looking at, trying to figure out what are major and minor products, first thing you look at is the substitution pattern. The second thing you look at is stereochemistry. All right? Okay, and there's something else related to stereochemistry that is actually not in this chapter. It is in chapter 11, but I think this is a good context for it, so I'm going to go ahead and tell you. And if you want to look it up in the book, I believe it is in chapter 11. That is EZ configurations. All right? EZ is going to be very, very similar to cis-trans. In fact, the E configuration is basically analogous to trans, and the Z is analogous to cis. Really, the only difference here is that E and Z refers to tri- and tetra-substituted alkenes, whereas cis and trans is just for di-substituted. All right, let me show you an example. Let's say we had this alkene, right? This is a tri-substituted alkene. Basically what you do is you look at each carbon. You know each carbon in the double bond is going to have two other bonds to it, right? This one, for example, I'll draw the H. It's got an H and it's got a methyl group. The one on the right here has a methyl and an ethyl. To figure out E or Z, here's what you need to do. Look on each one of the carbons, and of the two, assign a priority. Assign a priority just like you did in Chapter 5 with the RS configurations, right? Same rules. What gets a higher priority? Does the H or the methyl group? Well, hopefully you'll be able to tell that the methyl group is definitely a higher priority than H. So I'm going to put a number 1 by it. All right, and that's just for this carbon. Now we're going to do the same thing for this carbon. What has a higher priority? Methyl or ethyl? Hopefully you would know that ethyl has higher priority, so we'll put a 1 by it as well. If these two higher priority groups are on the same side of the double bond, that means you have a Z arrangement. However, I could tweak this a little bit. I just basically swapped places with the methyl group and the ethyl group on that second carbon. Right? So now, highest priority group over here is methyl. Highest priority group over here is still ethyl, but now the number ones are on opposite sides. That is an E configuration. So you see, very similar to what we did with cis-trans, except with more substituted alkenes. E, as you might expect, is more stable than Z due to steric hindrance. Okay, and so yeah, you can get into cases certainly whenever you're doing problems where you'll see EZ, cis-trans, tetra, tri, di, substituted, etc. All these factors can pop up. All right, here's an example. This is going to be an example where you actually have 3 potential products. All right, so if you take a look at this, all right, there's our base. Remember what we have to do. We have to identify places that have beta hydrogens. You have 2 spots that have beta hydrogens right here and here. They are different from each other. So that means you're going to be forming a double bond between those 2 carbons. And in other situations, you're going to be forming a double bond between these 2 carbons. Okay? All right, so here's the process I like to go about. I like to go through and do this and just figure out the constitutional isomers first. And then I go back and look, okay, could I potentially draw any stereoisomers based off the structures I have? All right? Well, if we look at the top one here, this is a mono-substituted alkene. We have not gone over any different stereoisomers that can be drawn with mono-substituted alkenes because there are none. This is it, so you don't have to worry about it. All right? Now, if you look at this one right over here, you'll see this is a tri-substituted alkene, and you can classify this one as being E or Z. Which one would it be? Well, highest priority group on the left carbon is bethyl. Highest priority group on the right carbon is ethyl. Whoops, don't mean to put a 2 there. In fact, I think this is the same one we just did in the example. They're on opposite sides, so that is the E arrangement. But if you have the E, it is certainly possible to have the Z as well, so that does need to be included as an additional product. So you would actually get 3 different products here. Which one would be major? Well, you know it won't be the top one, right? Because it's less substituted than the other 2. The top one's going to be the most minor one. All right, then you're looking at these 2, and the only difference is that one of them's an E, one of them's a Z. So we know that E is more stable, so we know that this guy is going to be the major product. All right. Any questions? No, everybody understands it? Good. Ha 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 ha. No, seriously, if you have trouble understanding this, let me know. I do want to make it clear that just because you have a di-substituted or a tri or a tetra, you don't necessarily always have cis-trans or EZ. For example, let's say I had something like this. Pretty similar to the one I just did, except we don't have an ethyl group, we have a methyl. All right? So if you're going by the priorities here, right, methyl's definitely higher priority than hydrogen, of course. But then over here you have 2 methyl groups, right? That's a tie. So there's literally no way that one of these can have priority over the other one, right? So in this case, you don't even have E or Z. Same thing over here. Let's say we had something like this. All right, so this one has a lot of different stuff. Oops, hold on, messed up. There we go. So this one has a lot of different stuff going on in it, right? We have an isopropyl group here, a methyl group here. However, on this side, again, we have two ethyl groups. So neither one of these can ever take priority. So this is a case where this would just be it. It's literally, if you took these two ethyl groups and swapped them out with each other, I mean, you still get the same arrangement, right? So in that case, then you don't get any stereoisomerism. Isomerism, excuse me. Cis-trans, you don't always necessarily get both stereoisomers. You might just get one or the other. For example, here, let's say you're doing this. You add a base, all right? And let's say, you get this as a product. You have two beta carbons with beta hydrogens here and here. They're exactly the same, though, so you really only have to pick one of them to work with. You would form a double bond here, right? Is this a cis or trans arrangement? Well, I think it's pretty obvious to say that this is a cis. Can you ever get the trans here? The answer, no, you can't. Reason being, we cannot freely rotate around any of these carbon-carbon bonds in your ring because they're locked. They're locked into a ring, right? So in this case, the only thing you could possibly get would be cis, and cis only. So there's certain situations you have to look at where they either the stereoisomers aren't present, or you just get one over the other because of certain circumstances. But otherwise, you do need to account for them. All right, I'm going to wrap it up there. That's a good introduction. Be sure to go through this, and I will get some Chapter 8 homework up and also start working on the next video. Until next time, hope you have a good day.